Now, so let's read the problem. A pond with an initial oxygen content of 0 is to be oxygenated by forming a tent over the water surface, and filling the tent with oxygen gas at 25 degrees centigrade and 130 kilopascal. Solubility of oxygen can be estimated from Henry's law, which is given, and the Henry's constant is given in terms of atmosphere. And XO2 is the mole fraction of oxygen in equilibrium with a gas which has a partial pressure of oxygen PO2. The diffusivity of the oxygen in water is given. There's a misprint there. It must be centimeters square per second, not centimeter per second. The units for the diffusivity must be length square over time always. Determine the mole fraction of oxygen at a depth of 2 centimeters from the surface after 12 hours. So let's draw a schematics of the problem. So you have a tent or maybe a chamber over a pond. Okay. This is the pond. This is yeah, so there is only oxygen gas here in the tent, right? It's at 25 degrees centigrade and 130 kilopascal. Okay. So initially, the concentration of the O2, let's say CO2, initially, let's call it Ca0, is equal to 0. Okay, there's no oxygen in the pond. And let's see how the oxygen diffuses and how much oxygen you're going to have after some time at a particular depth. Okay, so the Henry's constant is given. The Henry's law is written in terms of pressure. This is given as the partial pressure of oxygen in the gas. And this XO2 is given as the mole or equilibrium mole fraction of oxygen in water. Okay. And H prime is given as 4.27 times 10 to 4 atmosphere. Okay, so this is unitless, this is atmosphere, so this comes out to be atmosphere, so that makes sense. So there's no inconsistency with the units. Okay, so now, how can we solve this problem? This problem basically looks like our heat transfer problem where you have like semi-infinite wall, right? The heat is diffusing through a semi-infinite wall. Because actually the size of the pond is not given, but apparently we are curious about the oxygen concentration at the tiny depth, like a 2 centimeters depth. So you can assume that probably pond is going to be much larger than the 2 centimeters. So you can practically take the pond semi-infinite in this direction. Okay, so you can have this z is equal to 0 for the pond. This is plus c direction, if you like. And you can actually assume that the pond is endless and it goes up to infinity, just because we are curious about the concentration at the particular depth of 2 centimeters, which is very, very small, probably compared to the entire size of the pond. Okay. So we're gonna get a similar equation, but let's actually do our mass balance and see what kind of a differential equation we're gonna get, right? First of all, let's do the mass balance. Mass balance for the oxygen. Let's call it mole balance, okay? Let's call it mole balance for oxygen in water. Okay. Within a shell of thickness delta Z. Okay, so we're going to do a shell balance here. And my shell is going to be this. And I'm going to assume the flux Na is entering at Z, and the flux Na is exiting at Z plus delta Z. Okay. So we say in minus out plus generation is equal to accumulation. Okay, first question, is this a steady state or an unsteady state problem? What do you think? What is your opinion? Is this a steady state or an unsteady state problem?
Unsteady state.
Oh, okay, let's talk one by one. Okay, anybody who says unsteady state?
I think it's unsteady state.
Okay, anybody who thinks it's steady state?
I think it's steady state.
Domingos, why do you think it's steady state?
So since they are telling us like the tent, they're gonna put the tent and they're gonna give us some oxygen. I think they're gonna have like a steady state rate instead of unsteady state that's coming inside the water.
Yeah, but if you wait long enough, right, Domingos? If you wait long enough, yeah, it might come to the equilibrium and it might be steady state, would not change with time. But what does it say? See, determine the mole fraction of oxygen at a depth of 2 centimeters from the surface after 12 hours. What does that after 12 hours mean?
Oh, I see it now. It's gonna be unsteady.
So, yeah, exactly.
It's not like equilibrium yet.
Yeah, so initially you have 0 oxygen. So it's going to change with time, and it's asking how much of oxygen am I going to have after 12 hours. So this is going to be an unsteady state problem. Okay, so that's the first thing we should think about. The problem gives us the clue that things are changing with time. So I'm going to have an accumulation term. It's not going to be 0. But my generation is going to be 0 because there is no mentioned reaction, and you know that the oxygen does not react with water, it just dissolves in water. So you don't have any reaction. So there's no generation, no consumption. Okay. And in term is whatever is entering into my shell. This is Na at Z times the area, flux times the area, the rate of mass in, or the rate of mole in. That's at Z minus Na A at Z plus delta Z is equal to, the accumulation term is rate of accumulation, because I wrote down the rates here and here, so I should be consistent. So I'm talking about rate in, rate out, meaning that per unit time, and rate of accumulation. Okay. Rate of accumulation is rate of change of the amount of substance within my shell per unit time, right? So I write down the time derivative of the amount of oxygen. So the amount of oxygen is basically the concentration of oxygen Let's call it CA. Okay, let's call it CA because I'm using an A here. But I know that the A is O2. The concentration times the volume of the shell. The volume of the shell is nothing but the area of the shell times the thickness of the shell, right? That's the volume of a rectangular slab. Okay, so this is the amount of oxygen in the shell, right? And this is going to be the rate of change of that amount of oxygen. Okay, this is similar to what we have done in heat transfer as well, right? We were writing down the Cp times the energy within the shell, like Cp times the rho times the A times delta Z, right? If you remember, similar to that in that sense. Now, I can actually divide by delta Z, divide both sides by delta Z and A. Let's divide both sides by delta Z times A and take the limit as delta Z goes to 0. And you get minus d Na, well, actually, it's the partial derivative, del Na over del Z, right, is equal to del Ca over del T, correct? So this is like a similar technique that we used in the heat transfer as well, right? Now we should write down the formula for the Na. How can I relate the Na to Ca? Na to Ca. Remember when we did the heat transfer, we were trying to relate the Q to the T, right? Imagine we had an equation something like minus del Q over del Z is equal to del T over, but you had like something like Cp and so on there as well, right? Rho Cp del T. We were relating Q to the T by using the Fourier's law. Now this time, we're not going to use the Fourier's law. We're going to use the Fick's law to relate the Na to Ca. Okay. Use Fick's law. Okay. And formula that relates Na to two fluxes. One is bulk plus diffusive flux. And the diffusive flux term is going to be the Fick's law, right? As you remember, Na is equal to the bulk component, Xa times N, plus Ja, right? And the Ja from the Fick's law is minus dAB dCA, or maybe let's use partial differential del Ca over del Z. Okay. And we should actually compare the XAN and dAB del Ca over del Z, and you can immediately think about the low solubility of oxygen, and then you can argue that the bulk term is going to be, this term is going to be negligible. Okay, so you can say due to small solubilities. So oxygen in water, you can neglect the bulk term. Okay. In other words, Na is equal to XAN minus DAB del CA over del Z. We just get rid of this. Okay. Okay. Now the reason for this is because like when you think about this pond, right? The oxygen is dissolving and diffusing into the water, but it's going so slowly that the entire where is that? Yeah, the entire pond looks stationary. It's gonna like seem as if it's not moving at all, right? It's just the oxygen which is penetrating, and it's just like small. It's just that much, and from an outside observer, the outside observer is gonna see as if the entire thing is not moving. The average velocity of the entire thing is almost zero. Okay, so that's the idea. So we should only focus on the diffusion, the diffusive term. And so the Na can be approximated with the diffusive term, which is the Fick's law. Okay. Now I'm going to plug this in the original equation. Let's call this equation 1. Okay. Plugging this in equation 1, we get minus minus becomes plus DAB. First derivative done after another first derivative is the second derivative, del squared CA over del Z squared is equal to, and the right hand side is del CA over del T. So I got rid of the Na terms, and I only have the Ca as a function of T and Z. And this is my differential equation. Does that look familiar to you? Some constant times the second derivative with respect to position is equal to first derivative with respect to time. And I'm going to show you where exactly we had found this earlier. In unsteady state heat transfer problems. Yeah. Right. In the semi-infinite bulk case, as well as the other example. Let me show you. Where's the 7th one? Maybe this one is also good. Not this one. 7.1. Yeah, there you go. 7.1. Okay. So remember the shell balance we did here. This is unsteady state heat transfer for the general case without lump capacitance method. See, you have the second derivative of the temperature equals to 1 over alpha, which is diffusivity, times the first derivative of the temperature with respect to time. Well, actually, the formula that we obtained looks like this one. Instead of alpha, we have the diffusivity here, but again, it's still a diffusivity. Alpha was thermal diffusivity. Now this time we have the mass diffusivity in our equation, but other than that, and also instead of temperatures, we have the concentrations, but it's the same equation. So probably I'm going to have the same solution, but I need to have a condition there. I need to have the same boundary conditions to have the same solution. But this tells us the general solution should be the same. Okay, so let's see. Should go to this. Okay, and the way we solved this was so let me write down the boundary conditions first, right? The boundary conditions. The first one, at z is equal to 0, right? You can assume that once the water is in contact with the oxygen, it comes to the surface, just the surface, comes to the equilibrium immediately because it has a 0 thickness, right? It's just going to come abruptly to the equilibrium. So you can assume that Ca is equal to Ca saturation. We can call it CAS. Okay. The other boundary condition is at time is equal to 0. Initially, the entire pond has a 0 concentration. Another boundary condition, at z goes to infinity, I mean, far away deep inside the pond, you can assume that Ca is 0 within a short time interval. If you just think that I'm just interested in very thin layer on the surface, and whatever happens far deep under the pond is not going to affect my result, you can just assume that it goes to 0 as z goes to infinity. Okay, and this is very similar to the boundary conditions for the infinite wall case, right? In that case, we didn't have the t is equal to 0, but it was t minus t infinity, or t minus t infinity, which was 0. Similarly here as well, t minus t infinity. These two boundary conditions actually collapsed into one boundary condition, if you remember that particular example. And the first one at z is equal to 0, it was temperature was equal to the temperature of the surface. Surface temperature was kept constant. It's basically the same example, right? So the same treatments, let me go back, 8.1, the same treatments here will be valid. And if you think about our scaling argument earlier, we can do the same type of arguments and come up with the fact that the only thing that this concentration depends on is a combined variable called eta, and you can write it as the position z divided by 2 times square root of the diffusivity times the time. So using similar scaling arguments as we did before, using similar arguments we did for the heat transfer or unsteady state heat transfer through semi-infinite wall, like similar scaling arguments. We learned that concentration depends on a combined variable of z and t, which is eta is equal to z over 2 times square root of, it was alpha t, but this time my diffusivity in my equation, I don't have the alpha here. I have the mass diffusivity, which is DAB. So I have DAB here. Okay. In other words, CA is a function of eta only. Okay. And you don't need to have another like additional z or t dependency. So we say that CA is a function of eta, and you can just write the CA as a function of eta without using the t's and z's. Okay, so what does this tell us? You actually do the same type of analysis, right? And you write down the del CA over del Z in terms of dCA over d eta, and similarly del CA over del T in terms of dCA over d eta. And after simplifications, a similar analysis will give you the following equation. D squared CA over d eta is equal to some constant times exponential negative eta squared. Oh, sorry, I'm sorry, I wrote down the solution. My mistake. Yeah. Del eta squared is negative 2 eta dCA over d eta, similar to d squared t over d eta square is equal to negative 2 eta dt over d eta in heat transfer case, right? And you use the boundary conditions now. The boundary conditions might be a little different, but this equation is still valid. But before that, as we did before, right, you can actually assume that dCA over d eta is some other constant of eta. Let's call this g eta, right? Remember, we use the same technique. And the left-hand side becomes the first derivative of g eta minus 2 eta g eta. Okay. From here, the g eta over g eta is negative 2 eta d eta. And you take the integral of both sides, and you get logarithm of g eta is equal to negative eta squared plus some c prime. You take the exponential and you get g eta is equal to some constant c times exponential negative eta squared, as we did before. And the g eta is, as we described here, it's dCA over d eta. Now you can solve for the CA, and the CA comes out to be, yeah, you take, let's do it one by one. dCA is c times exponential negative eta squared d eta. Take the integral once again, and you get from, for example, eta is equal to 0 to any eta. And at eta is equal to 0, CA is equal to, that's my boundary condition. Since eta is z over this, taking z is equal to 0 makes eta 0. So it's this first boundary condition. So at eta is equal to 0, CA is CAS. And at eta, CA is going to be CA eta. Okay. From here, you find that, oops, CA eta minus CAS is equal to C times integral eta is equal to 0 eta exponential negative eta squared d eta. And let's note it. Note we use the BC at eta is equal to 0, meaning that Z is equal to 0. CA is equal to CAS. Okay. Now let's use another boundary condition here. Let's have a look at these two boundary conditions. So when t is equal to 0, you see, eta goes to infinity. Similarly, when z goes to infinity, eta goes to infinity. So both of these boundary conditions means for eta goes to infinity, CA is equal to 0, right? We use this thing to actually come up with this. So that's our second boundary condition. We know it from our previous analysis that these two boundary conditions collapse into one, right? BC2 at eta is equal to, sorry, eta goes to infinity. CA goes to 0. Okay. So let's plug it in the equation. We get the following. 0 minus CAS is equal to C times, we want to find out this constant C. That's why we're using this boundary condition. From 0 to eta goes to infinity, exponential negative eta squared d eta. We know that this integral is square root of pi over 2, right? As we did before. Let me show you exactly where we did this. See, it's the same actually type of mathematics that we're dealing with, right? And here you can solve for C. C comes out to be equal to negative 2 over square root of pi CAS. Now plugging in this value, okay, plugging this value in, and let's call this one equation 2. Equation 2, we get CA minus CAS is equal to negative CAS times 2 over square root of pi integral from 0 to eta exponential negative eta squared d eta. And here basically you can use a dummy variable instead of eta, right? Let's say minus, I need to make up some letter here. Let's say S. Yeah, because I mean you're gonna plug in back eta. That's why I just don't want to use the same variable. Okay, that's okay. Either way is fine. But so if you divide both sides by negative CAS, then you would get 1 minus CA over CAS comes out to be 2 over square root of pi S squared ds. And this is what we call as the error function. Error function. of eta, right? If you remember. And 1 minus CA over CAS is error function of eta, where eta is z over 2 square root of dAB times t. Now, okay, it's easy peasy now. If I know the z, if I know the t, if I know the dAB, I can calculate eta and I can plug in this equation and I can solve for the CA. So that's it. That's what we're gonna do now for our problem. For our problem, dAB is given as, let me pick up the numbers. Where is that? 2.42 times 10 to negative 5 centimeters squared per second. You need to convert it into SI units, which is 2.42 times 10 to negative 9 meters squared per second. And time is after 12 hours, right? 12 hours. In SI units, it's 12 times 3,600 seconds, which is 4.3 times 10 to 4 seconds. And z is, so it's a depth of 2 centimeters, which is 0.02 meters. Okay, so eta comes out to be 0.02 meters divided by 2 times square root of 2.42 times 10 to negative 9 meters squared per second times 4.3 times 10 to 4 seconds. And this comes out to be unitless because the seconds cancel. The meter square becomes meter when you take it out of the square root, and it cancels with the meter. And the result you get is, let me check my notes. The result you get is something like 0.98, I guess. And the error function comes out. So I can use this formula, 1 minus this one, CA over CAS is error function 0.98. And this is approximately 0.842 unitless. And then CA over CAS comes out to be 1 minus that value, which is 0.158. So you get basically a little more than 1/10 of the, or maybe, what is that? You get actually 1/6 of the equilibrium concentration. But the problem asks you to find out the XA. What is XA? Well, actually, XA is CA over total concentration, C. Okay. So you can write down that XA over XAS is the same thing as CA over C divided by CAS over C. You can cancel these C's and you get CA over CAS. Well, you already found it, which is 0.158. And now this tells you that XA is equal to 0.158 times the XAS. So if you know the XAS, then you can calculate this XA at 2 centimeters depth. XAS is the equilibrium mole fraction, right? So XAS can be estimated from solubility data, given in the form of Henry's law. Okay, so the equation that the question provides is PO2 is equal to H prime X O2, but it's basically XAS. Okay, that's the solubility mole fraction. It's given in the problem as solubility mole fraction. So from here, XAS can be written as PO2 divided by H prime. The PO2, the entire thing is the oxygen at 130 kilopascal. 130 kilopascal divided by H prime is 4.27 times 10 to 4 atmosphere, but you need to convert the atmospheres to kilopascals. So 1 atmosphere is 101, I guess, 101 kilopascal, right? And you get the XAS as, let's calculate, 130 divided by 101 divided by here. So it's basically 3.01 times 10 to negative 5, right? That's the XAS. Okay, so the XA comes out to be, using this formula, 0.158 times the XAS, 3.01 times 10 to minus 5. And you get XA is equal to 4.76 times 10 to negative 6. This is the mole fraction of oxygen in the pond at a depth of 2 centimeters after 12 hours of exposure. Yeah. Okay, so that's it. You have any questions about this problem?
How did you know it was a semi-infinite slab?
Oh, that's a great question. So basically, the pond size is not given, but I assume that the pond is much larger than this 2 centimeters. Okay, so I assume that the surface of the water, the molecules near the surface of the water does not feel the other end of the pond because it's actually far away. And it's just the relative size scales that actually makes me make this assumption of infinite slab. Does that make sense?
Yes, thank you.
So you can do similar assumptions for the thermal, like the heat transfer as well. You can actually heat up a wall from one side if the wall is too large and you're talking about like either short time intervals or maybe like temperature near the surface, then you can make this assumption. Because, yeah, in this case, I know that, I mean, the pond is going to be orders of magnitude like deeper than 2 centimeters. Okay. It's going to be, even if it's, for example, like 2 meters, it's like 2 orders of magnitude deeper. So, and I know that the diffusion is so slow. The diffusion is so slow, and the end result also actually gives you an idea about that. I mean, it's with this assumption within this thickness, right? The concentration at the depth of 2 centimeters, even 2 centimeters, is almost like 6 times smaller than the surface concentration. So it's like changing very sharply. Okay. So you can, I mean, there's no harm in taking the pond infinitely large. Any other questions? And the other reason is actually the size of the pond is not given, and I have no other chance than choosing it.